Good morning, everyone, and welcome to day 3, the final day of the Summit on Geophysical Detection of Explosive Remnants of War, Solving Current Challenges of Unexploded Ordnance and Demining. Today, we will hear from 2 organizations attempting to attract like-minded geophysicists to share in mentoring of knowledge associated with the physics of ordnance detection. We will also have a presenter outlining detector platforms specifically designed to efficiently work in their local operational environment. Additional talk will utilize fuzzy logic to the task of determining whether to harvest recovered explosives or dispose of the ordnance. And this will be followed by a rather intriguing discussion on using convolution neural networks to classify UXO directly from EMI data. And then a final talk on full waveform inversion of GPR data. I am Bob Selfridge, Chief Geophysicist for the Corps of Engineers and for the Engineering Support Center, Huntsville, and I will be co-chairing today's talks with Matt Guy from Geomatrix Limited. Matt?
Thank you, Bob. Each speaker will have 15 minutes to give their presentation and then 5 minutes for Q&A. Any speaker who goes over the 15 minutes will cut into their Q&A allotted time. Please place questions in the Q&A box, which you can find at the top panel bar on your screen. After 20 minutes, the speaker will be asked to answer any questions during the discussion and answer session at the end of the day, when the floor is opened up to attendees to raise their hands and unmute and answer questions directly.
And with that, Matt and I would like to introduce today's keynote speaker, Christopher Virgil, who is going to introduce us to his vision of the working group on ordnance detection of the German Geophysical Society. All right, Christopher, the ball is in your court. Thank you.
Thank you. Okay, so in Germany, we have a severe issue with bombs from the Second World War. Not only on bombs, but also ammunition from the Second World War. We heard a little bit on this topic from Jan on Tuesday. And in a sense, we have still a lot of bombs, roughly 200,000 buried in German ground. And here on this slide, just a reminder about the destruction, which basically happened around, in all the bigger cities in Germany, not only in the like Berlin, Hamburg, Köln, or whatever, and also industrial complexes were destroyed, rail tracks were destroyed, highways were bombed, and so on. So it's an issue which affects the whole countryside. And with the destruction, of course, there's a highly probability to find unexploded ordnances in these areas. So to give you some numbers, it is estimated that in the city center of Berlin alone, roughly 4,600 unexploded bombs are still in the ground, and this endanger the public. And these unexploded ordnances and ammunitions pose a severe problem, which is indicated by the accidents happened every year. So, for example, from the end of Second World War to roughly present day, there were over 1,200 accidents happened with ammunition involved. So exploding bombs on construction sites, or other live ammunition found in the ground. There are even 1 to 2 spontaneous explosions where bombs without any manipulation suddenly explode on the ground, mostly due to long-time fuses in these objects. Okay, so how do we deal with this danger in Germany? So here you see a schematic overview about the procedure which we follow to do the UXO clearance. So if you have, for example, construction site in a city which was bombed or which was fighted for, then you have to be clear and have to be sure that there's no ordnances in the ground buried. And for this, the first phase would be historical research. So as Jan showed us, there were aerial photos where the bomb crews or bomber crews took pictures of the results of the bombing runs, but there are also other documents like whatever information about fighting or positions of troops and so on. So there's a lot of information you can refer to in order to see if there was any or there could be any potential danger in the ground nowadays. And if you have done this evaluation of the historical research data, you will get either the information, okay, there is quite probably no danger in this area, so there's no indication for danger at least, and then you could get the permittance to do whatever you want or what is proposed on this land. However, more often the suspicions could not be dispelled, so there's not you get not the clearance to work as intended, but you need to go to the second phase, which deals with the technical exploration. And this technical exploration, of course, means we need to do surveys with different geophysical methods in order to see if there is any immediate danger or if there are any unexploded ordnances. Based on this data, we do a risk assessment and basically analyze the data, so to see if the objects we might find are of could be some exploding ordnances or just some minor debris or whatever. But again, the normal approach is that we could not give this answer from the data alone. So we could not say, okay, there are objects or stuff found, but there are definitely no bombs. So the next step would therefore be the clearance of the potential ordnances. And this enters the third phase. If you are going to do this clearance, you first need a very detailed clearance concept. So you need in detail plan what to do. So this also includes an estimate about the size of the object or the danger potential of this object. Is it a small grenade or is it a bigger bomb? So, for example, for questions like the evacuation, do you need an evacuation of the surrounding, and how much should be the area of the evacuation? But also, what effort you need to do for the clearance. So, do you need a big hole? Is it how deep is the object? Do you have groundwater there? All these information must be included in this concept, and also then you need to tender and awarding the contracts to the actual clearance companies. And well, if you finish this concept, then the actual clearance will the object will be digged out, and if it's a bomb, and it will be either diffused on site or transported, or if it's necessary, detonated on site, which of course requires another amount of work and preparation. Okay, so what are the challenges here in Germany for the ordnance detection and clearance? First of all, we have very different kind of ammunitions here in the ground due to the Second World War. So it ranges from small scale caliber ammunitions to different kind of landmines, anti-personnel and anti-tank mines. We have different grenades, either hand grenades, mortar grenades, tank grenades, and of course quite a huge variety of different bombs. So we have these explosive bombs, the bigger explosive bombs, but also smaller incendiary bombs and bomb droplets and so on. The second point is we have to do the clearances and the surveys up to 10 meters, or in some cases even beyond that. So we usually, especially when we suspect bigger bombs, we cannot just use surface magnetics or surface georadar or whatever. And the last point is that very often these suspected munitions are located in urbanized areas, so where we have strong interferences of our measurements by clutter or the environmental situation. So how do we go on then with a technical exploration? Basically, we use the classical three methods: magnetics, electromagnetics, and GPR. But in order to cope with a higher induction and higher depth of investigation, we have surface measurements combined with bowl systems or bowl measurements. So of course it depends on the suspected ammunition type and the proposed construction you would like to have on these of these areas. But the typical approach would be first do surface surveys and afterwards the bowl surveys. And that again depends on the situation. If you have a lot of clutter or interferences, like in the city center, you are, for example, limited to mostly georadar. If it's a more open condition or without any debris, for example, something like that, then of course you can also apply magnetics. So it's quite depending on the circumstances. Okay, so but why do we need a certain working group or additional working group on this topic? The methods I presented to you are basically purely on geophysical methods. So we need, of course, a strong geophysical background to understand these methods and to develop these methods. But there is, interesting enough, no centralized geophysical institution like in a university or so, which is dedicated for the research in this field, at least not in Germany. So there are, of course, working groups inside the different universities and in different research institutes which are working in this field and developing methods, but it's not quite, you can say, centralized and not very well led. And this leads that the findings and advances we do as geophysicists in these fields very hesitantly used in the field of ordnance detection and clearance. And the last point is this important field of work of ordnance clearance and detection does not play a major or even a minor role in the education of geophysicists in Germany. So it would be very nice if this would included in the actual lectures that the students hear along their studies. And in order to cope with these problems, we founded our working group in 2002, and we are part of the Geophysical Society, the German Geophysical Society. So this is the largest association of geophysicists in Germany. So we have a strong geophysical background in this working group, but, and this is important, we are not only geophysicists, but we include a lot of other expertise in our working group. So we have different universities with us, but we have also the clearance companies, which are part of our working group, different stakeholders, other research centers than the universities. We have engineering offices, device manufacturer, and also some federal institutions there. So we got information and ideas over the UXO clearance from all sides or from all points of view. Well, and we will meet 2 times a year. The first one would be the annual meeting in March, the annual meeting of the DGG in March, where we discuss stuff for half a day, and a more, could say, productive workshop in the autumn, roughly around October, where we really work on stuff. So where we do whatever writing papers and proceeding with our ideas. And the goal of this working group is to increase the effectiveness of exploded ordnance clearances and to improve the safety for the stuff which works with methods, but also for the general public around these sites. And with my last slide, I give you some more detail about our ideas how to improve the situation. So basically we have 3 columns and 3 points of interest here. The first one deals with the methods itself and with the background of the methods. So in general, as I mentioned, we use magnetometry, radar, electromagnetics, and so on. But we would like to further develop this these methods, and also try to include actual research and current research from our geophysicists into this topic to develop new methods, or at least to further develop the old ones. And then another very important part is the creation of guidelines. So it's hard to imagine, but in Germany there are no official guidelines, for example, when to use which method. So in which, under which conditions you should use, for example, magnetics. And this leads to problems when some decision maker need to hire a company, a clearance company, for example, for doing surveys, but have no background in geophysics. So this decision maker needs to rely on the information the company gives them. And if the company is, how to say, either not able or not willing to do proper measurements, then you have a problem. For example, if the company assures you that the surface GPR is enough to give a clearance up to 8 meters, and you as a decision maker will believe this company, you will get the job done, no question. But there's no guarantee that the construction site, for example, is actually free of any hazardous objects. And there were some issues in this case where accident happened after a company gives the clearance. So if you have a guideline on your hand, which really describes how the method works and under which conditions you can apply these, and maybe where are the limitations of the method regarding depth or environmental surroundings, then you can do your decisions on a much better basis. No? And also it helps the people who actually operate the systems to see, okay, where are the issues, what have I have in mind to work with a certain method. But also we would like to improve the situation in software. For example, we would like to build up a database where we include measurements, actual measurements or test measurements, and also numerical simulations of complex UXOs. So, for example, a numerical model of explosive bomb and the resulting magnetic anomaly. And of course, yeah, when we are talking about software, of course, also the processing software is an issue. Could we use our background to improve existing software, or yeah, at least give advice how to do this? The second column would yeah, deal with the knowledge transfer and the networking. So here the biggest issue or the biggest question is how to bridge the theory and praxis. So we would like to bring the university and the research together with the companies which are doing the work in order to yeah, part in our ideas and information we have to yeah, strong to increase the research in these topics and to increase the knowledge in these for these methods. And the last part would be.
You, but you're coming up to the end of your time.
Yes, thanks. It's okay. The last few sentences. We would also like to include this topic of unexploded ordnances in the actual studies of geophysics in the universities, in order to connect the students with the company, but also to give the universities opportunities to yeah, to have larger collaborative projects with these companies, and for example to yeah, give thesis in the field of unexploded ordnances. Okay, so then with this I will close now, and I will thank you for your attention, and you will find us here. So if you have any questions further on, further to the question round afterwards, then you can find us here. Thank you.
Thank you, Christopher. Thank you very much. We do have one question, but I think we're going to have to hold that back for the Q&A session at the end of the day.
Sorry.
But thank you very much.
Our next speaker is Mike Anderson with Aptum Federal Services, and he'll be speaking on data acquisition platforms for munition response projects. All right, Michael.
So as it says, this is just a very non-technical discussion here on some of the acquisition platforms and munitions response. You know, we've seen some great presentations on data flow, and some of the sensor technology. But at the end of the day, the data has to be acquired, and there are very few sites that don't have unique challenges. So, you know, this is what I'm going to sort of discuss here, and some of the things you can do to better your data quality. You know, certainly, there's emerging technologies, advanced geophysical classification, drone technology, but you know, there's a munitions response geophysical toolbox, and I don't think that will ever go away. And, you know, each site is unique for depending on weather conditions, terrain and topography, your target of interest changes, the depth of the target of interest, and former and future use are all considerations when you're selecting a certain technology, a sensor technology, and a deployment method. So I like to think that there's a toolbox, and there's no one fit all, and some are better than others, but we do have to respect that that there's a toolbox to select from. Now, before the survey even starts and data is collected, you know, for the field geophysicists out there, I just want people to be aware of how involved this is. These are big systems. There's lots of moving parts, lots of equipment, and before the data is ever collected, there's the management of the boxes, and each survey is an exploration. It's a geophysics munitions response, as much as any, is a very applied science. And again, we sometimes focus on the pretty pictures and the analysis, but none of that's possible without the data collection. I'm not going to talk too much about drone. We've talked a lot about drone, but I did want to mention that before drone, there was HeliMag. And this was extremely good systems. I worked on several of these projects with the companies that produce these airborne magnetometer systems, and they were extremely good at what they were for, which are larger items and wide area assessments. And I think that at some point that kind of got lost, and people thought, oh, well, 500 acres in a week, that's the way to go. And they didn't respect the toolbox and try to make it a one fit all. And I don't want that to happen to drone. Drone's a great technology, but and maybe the more popular choice in the toolbox, but it's also got limitations. So I'm just going to briefly discuss some of those. I do like the fact that there's no operator. In the next slides, you'll see that as a field person, safety is a concern, and you want to minimize footprint, both for safety to the operator, but also environmentally. There's less of a footprint, literally. Drones can get to hard to reach areas. That's where I have some experience with drone in the munitions response industry. We did transects in the mountains of Utah, where it was just not safe to go, and it was a successful survey. We were affected by some of the cons that I'm going to mention, but it did serve the purpose of reaching hard areas. The data quality can be really good from drones. I love free air data where the sensor is actually not touching the ground, or the acquisition system's not touching the ground, and not affected by surface noise and bumps. So airborne data can be really good. The HeliMag systems that I showed you were extraordinarily quiet, and therefore it could detect a signal of 1 to 2 nanotesla was a valid anomaly. And you can get good production with drones, we know that. But some of the cons are weather. It is weather sensitive, mostly wind, and that we found out. So we were limited to kind of mornings and evenings. And then the sensor detection. At the end of the day, the sensors may change, platforms may change, but the laws of physics aren't going to change. And you have to be a certain distance from an object, or you're just not within the magnetic field of the object, or in EM sense, you're not within the current of the object. I will refer to drone in a bit, because you'll see some places where it was probably applicable but just wasn't around. Traditional ground magnetometers, they're reliable and easy to use, and they have deep detection. Again, this is non-technical, so I'm not going to get into why they detect deeper than some of the electromagnetic methods, but we can talk about that in the question and answers. Magnetometers are a passive method, and for the non-geophysicists out there, that means that they are simply measuring a magnetic field, an existing field, versus active methods. The EM methods are active methods, and they actually have to transmit energy into the ground so that they can induce eddy currents. Now, what does that mean in a nutshell? It means that magnetometers essentially need no power. The only power they need is to actually record the data and convert the data into a numerical value, whereas EM systems actually have to transmit data and require batteries. And the batteries can be heavy. We'll see some of the AGC systems, they get a little bit bulky. But that's the basic difference. Here's an EM system, a ground EM system. I think a lot of us know this one is the EM61. I'm not going to mention too many manufacturer names, but this one's fairly obvious. It's extremely versatile. It wasn't developed for munitions response, but based on the time gates that it has, the measuring units that it does, it's very good for measuring, detecting munitions, which are typically 0 to 5 feet in the ground. So it's got decades of success. It's very versatile, as you can see. Here are some other examples. It can be pushed on an inner tube. It can be pushed along snow in a sled, and it can be constructed in a rickshaw fashion and pushed and pulled. So that's there's some other ground methods. Not wanting to go to the next slide here. There we go. Some other ground methods are the AGC methods. So this is an advanced geophysical classification. And again, when we think of the toolbox, this is certainly or arguably the most powerful tool in the toolkit, and is highly recommended wherever you can use it. These systems are highly intelligent. They acquire really robust data. I'm not going to get into the technical part of it again, but they serve as advertised. So certainly more favorable than some of the older methods. But again, just a tool in the toolbox. You can see all the batteries. They're substantially heavier and therefore more limited in some of the terrain that they can be used. There are sort of stretcher and cart modes for tougher terrain. So with a little ingenuity, they can be put together and operated in rougher terrain. Here's some other AGC systems. Again, a little bit bulkier, but huge cost savings in terms of not digging up unwanted frag and less environmental impact. This is an AGC system that's used for queued analysis. In other words, there's a survey done, we have a set of anomalies, a list of anomalies, and we actually go to each one and take a queued reading and an analysis from that queued reading. The other systems can do queued stationary readings and dynamic. In other words, they can classify well in a well moving. There are handheld AGC methods. These are used primarily in sloped areas and then in wooded areas where you couldn't fit one of those carts that I showed you. On to towed arrays. So again, we're looking at a toolbox. And if you can use a towed array, you'd want to use a towed array. It's safer for the operator, free from biohazards, less fatigue, and often the data can be better because the sensors can be more stable than walking, which causes an up and down motion. These are two examples. There's a sled array, which is literally dragged along the ground. Some points to note is that they can be stable, very stable versus wheels. And then I wanted to point out some of the things that you would look for in your tow system would be a quiet engine. So in other words, you know, that we obviously have metal detectors, and so they will pick up engine noise. And so you want a quiet system that doesn't have a lot of a shell, a metal shell, and an alternator. The alternators are very noisy, and so typically we use diesel-powered vehicles that don't have an alternator. You know, some of the other things to look for are the conveniences, although they're not. They're necessities when you're in Florida. So this system was great, but it had no air conditioning and essentially couldn't be used in the summer in Florida. The Kubota is also a good system, but it's limited to flat terrain with these wheels. And what we found is that it couldn't really operate at slow speeds because the clutch would burn up. And so those are the kind of things you look for when you're operating in towed vehicles. Here are some other examples. The Polaris, and then an autonomous system. Pros and cons. The Polaris is great system for towing, but it has wheels, so you wouldn't want to operate it anywhere where you had mud. Some other more interesting systems, and of course this is Canada because they love their wood, and so those are the whole back part of this wood structure are magnetometers, and that was the infamous mud buggy. Actually collected really good data. There's some more Canadian wood. There's our other ground systems. You can be creative. Magnetometers do not detect aluminum, so this system was fixed with a aluminum ladder that served multiple purposes. Here's where drone might have been a good idea. This was, you know, about 6 years ago, and drone technology just wasn't there. We actually tried it, but it just wasn't there in terms of the ability to track lines. So this system here is used for cutting around power lines. So the pole is non-magnetic. And so we strapped on a magnetometer array, transmitted the data to the cab, and we're able to reach this doesn't show it fully extended, but we were able to reach some hard to reach areas like you see in this photo. Back to those two systems that we had, they didn't quite make it. And again, it's just a lesson learned. Everybody was okay, but you can lose a lot of time if your acquisition systems aren't up to the task. We quickly went to and again, this is the only other name that I'm going to mention because this thing saved our 5-year project, is the SHERP. This is the best towed vehicle I've ever used. It's covered, it has air conditioning, room for equipment, it floats, it's extraordinarily quiet magnetically, so you can use a really short tongue. And it's got lots of room inside for storing the equipment, and it can drive really slow, especially the AGC sensors where you really want to go really slow. It can be taxing on a tow vehicle. So make sure that you have something that can go slow, and also something that can house a navigation system so that you have your straight lines. Here are some of the AGC sensors in towed form. And then there's shallow marine surveys. Shallow marine surveys are the big challenge is, again, maintaining a straight line. So sometimes you might want to have ropes attached to your system to make sure that it goes in a straight line. Little deeper surveys. I just want to show that with the correct navigation, you can really get that straight line, and you need it. Just in marine, any type of wind, and you're going to be offline and not get that quality data. AGC is coming to the marine environment, as you see here. And so, again, anytime you can use AGC sensors, I would recommend it. Positioning systems are also advancing. This is the SLAM, the Simultaneous Localization and Mapping System. It's called SLAM, and it's allowing us to map in woods. Again, I'm out of time, but this is an excellent advancement in munitions response. It can also obviously be attached to the AGC sensors. I don't have time to talk about automation, but it's there. But again, I caution it just being another tool in the toolbox. Our guys were real excited about the robotic dog actually replacing them, but I don't see it happening anytime soon. And at the end of the day, there's still going to be the need for creativity and resilience in geophysics. It's just that kind of science. It's many reasons why I got into it, and it's many reasons why people get out of it. It's you have to be creative. It's the epitome of brains and brawn and ingenuity. Just to conclude, just remember the old slogan, garbage in, garbage out. So if you don't get good data, we're not going to get the pretty maps and the analysis. The keys are sensor selection and deployment methods. The upper right picture is myself with a Tiny Tim rocket that was found 14 feet below the surface in downtown Orlando, Florida, a major U.S. city. And it was found using magnetometer, where we had surveyed with the EM61 to remove clutter. We went with the magnetometer and we were able to detect that. So again, remember sensor selection when you do these surveys. Thank you.
Thank you very much, Michael. That's great. And I must admit, I'd probably suggest changing the title of your presentations to Brains, Brawn, and Ingenuity, because that's certainly a good caption.
Thank you. Thank you.
And I did like your comment about it's the reason you got into it and a reason why many people are getting out of it.
Yeah.
So that was a great summary of all the different, and I have personally, I've been in business for 40 years. I had never seen the Canadian wood structures before for surveying. So that was excellent. So, all right, we're going to move on to the next talk. Thank you again, Michael.
Thank you.
Our next talk is Andrew Alling, and he's talking on exploring collaborative solutions for unexploded ordnance detection in iron-rich environments, a vertically integrated projects approach. And I should mention, anybody that has questions, please find the Q&A app at the top of the screen or wherever it is showing up on your screen. Hit that Q&A button and enter your comments and your questions into there. So as we coming up to a break, and we will try to take as many of those questions as we can, both at the break period and at the end of the day. So with that, Andrew, the time is yours. Thank you, sir.
Okay. Well, good morning, everybody. My name is Andrew Alling, as I was introduced. I'm at the University of Hawaii at Manoa. I'm a sophomore in electrical engineering and electrophysics. And I'm going to talk about University of Hawaii's newest vertically integrated project. So a little background. The problem that we have here in Hawaii is much like we've been hearing the past couple of days, where there's a lot of unexploded ordnance here. Particularly in Hawaii, we have 120 FUDs, or formerly used defense sites, which is kind of a high amount for such a small area. And over here, I have a scrolling list of all of the FUDs that are in Hawaii. Most of the FUDs here are the MMRP program, the Military Munitions Response Program. So most of them are because of unexploded ordnance, a lot from military testing around World War II. There's currently cleanup happening in these sites. They consist of small manned teams. They use EM61 detectors like we've been talking about, standard advanced geophysics, and they also utilize a MineLab Explorer 2 metal detector, which I'll talk more on in a little bit. So I'll just show a few quick examples of some of these sites. Here you can see, for the people that are not aware, the Hawaiian island chain. There are 8 main Hawaiian islands. This one, Makanalua bombing range, is on Molokai. It's 900 acres. Molokai is a small island, but it's still inhabited. And there's areas like this where people cannot access. We have Pacific Jumbo Combat Training Center. This is Kahana and Oahu. Oahu is the most populated Hawaiian island. It's where the capital, Honolulu, is, where Waikiki is. It's where I am at the University of Hawaii in Manoa. And then Waikane Training Area, also on Oahu, really close to Kahana. And right here is a picture of some of the survey teams going to this area. So you can see that, you might imagine, it's really jungly and tropical in a lot of these areas. And actually, I specifically chose Waikane because I have personal friends who are farmers who live in Waikane who are affected by this issue. There's hot spots on their land that they're, advised not to go around because it hasn't been fully cleaned up yet and it's affecting their lives. So in the face of this problem, the university has decided to create a new vertically integrated project. Now, what is a vertically integrated project, or a VIP? It's an educational initiative which actually started at Georgia Tech. It integrates undergraduate and graduate students into long-term research projects. So it follows a very standard model. We have faculty mentors, graduate students, undergraduate students, and multidisciplinary people in the project. So we'll have various different majors: electrical engineers, mechanical engineers, geologists. And these projects are supposed to be long-term, 5 to 10 years, and large projects, and we conduct academic research. And this really is the university's way of addressing issues in Hawaii. If you want to look at more of our projects, I encourage you to look at the link. The coral test bed is one of my favorites. It's really interesting. Now, to swing back to the issue, this project we're starting focusing on Waikoloa Maneuver Area, which has actually been talked about once already during this summit. Waikoloa Maneuver Area is a former testing site. It's one of the largest FUDs in Hawaii. Well, it actually contains 23 separate FUDs. All of them are MMRP. It's 100,000 acres. And in this map, you can see, this is from U.S. Army Corps of Engineers. This is the map of the area. And all of those red dots are all found munitions. And so you can see these green stars along the coast. I'm just highlighting some population centers. So those are all resorts. Waikoloa Village is like a neighborhood that people live at. You have an airport, Waimea Kohala Airport. And then you also have Waimea Town, which has communities, schools, grocery stores. Waimea Town actually has an elementary school that a few years ago they found 20 grenades right next to the playground. So this is just highlighting that this is a big issue in this specific area. So now I'm going to start talking more into the geology of this place, and I will apologize up front. I'm not a geologist or a geophysicist. Like I said, I'm studying electrical engineering, so bear with me on the specifics. But Hawaii Island, or the Big Island like we call it, is on the Waimea Plains. They were formed by volcanic lava flows, and it's also the newest island, so it's only about 400,000 years old. It sits in the saddle of 2 inactive volcanoes, which gives us a lot of geological issues, specifically with the iron-rich environment that we're seeing with the teams and the sensors that they're getting. So in Hawaii, the volcanic rock forms in this basaltic form, and it has a lot of magnetite in it and other iron-containing materials. And so here's an image of these rocks, and in the orange circles are little pieces of magnetite or iron. And so we're seeing that when the teams are out with their sensors, they are picking up what they think is a large piece of metal, so like what could be an ordnance. And then when they take all the precautions to dig it up, it's actually just a large iron rock. So it looks like a piece of actual metal, but it's really just a rock. And then also on top of these large pieces of metallic rocks, the iron oxide is homogeneously distributed throughout the soil, which generates a lot of background noise for our detectors. So they're looking for metal in a sea of metal and finding giant rocks of metal. And then I'm going to cite this study conducted on Kaho'olawe, which is another main Hawaiian island chain. This was done in 2008. They sampled various areas around Kaho'olawe, and they found that not only is it rich in iron, but they would take a sample from one 30 meter by 30 meter subplot, and it would vary significantly in its magnetic susceptibility to another 30 meter by 30 meter subplot not that far away. So even if we're able to classify the soil in one area to try and help remove the background noise, we're finding that you go over to the next plot and you're going to have to do it again. So these are some of the results from that study on Kaho'olawe. I'm going to highlight the iron specifically, or I would like to mention that this slide, they went to Waimea and Waikoloa. They were not able to dig, they were only able to take surface levels. So the iron oxide is not too high. But on Kaho'olawe, where they were able to dig, we're seeing very high levels of iron, almost 50% in some cases, which is really, that's what's messing with all of the sensors. So as part of our new project, we're still in the beginning. We conducted a literature review. In our literature review, we highlighted, okay, what are all of the available sensors and being investigated, and what should we investigate? We determined, or this is a list of the technologies that we decided we would like to investigate. The top two we decided are not a good idea for various reasons, but after day 3 of this conference, we're seeing that GPR magnetometers and EM detectors are the way to go, which is kind of what we've indicated at. The green means it's good, the yellow means it's medium, and the red means it's not good for our range resolution. So what's our goal for this project? We want to increase, we have 2 goals, short-term goals. One of them is that we want to build a test bed, and this test bed can serve multiple purposes. So in talking with the teams at Waikoloa on the Big Island, we've actually been told that with even with the AGC and the EM61 detectors, the metal is really giving them so much issues. And the number one piece of equipment that is helping them the best is this kind of old MineLab Explorer 2, which was discontinued in 2006. We've been told that this detector, if you give it to a highly trained operator, so somebody that has used it a lot in the past, they will be able to tell the difference between a hot rock and a UXO than if you give them another detector. So one of our goals is to develop this test bed, take a MineLab, and be able to test it on simulated targets and non-UXO metallic rocks. And this is an example of the controls that we would like to have for one kind of test bed like this. And then test bed 2, or test bed path 2, is to research other methods of detection. So here is just an AI generated image of what we imagine to be some kind of this test bed. And we want to explore different solutions. So improved technologies for our detectors, like improved coils, stabilizing sensors to keep the sensors level with the ground. And then perhaps being able to get other sensors like ground penetrating radar, the advanced geophysics, EM61, and combine them together to rule out false positives. And then we have our automation and machine learning aspect of it. So ideally we have this test bed and we're able to investigate various different kinds of detectors automatically. So we can control the speed, the angle of the detector, the height above the soil, the type of soil, the depth of the buried object, different kinds of buried object. And we can run these tests automatically all the time. And with that, we can build a high volume data set that we can plug into some machine learning algorithms. And with these algorithms, we can train a model that are on the advice of these experienced operators that could help an operator discriminate these types of objects maybe faster than they would without the model. So I'm going to wrap up a little bit shorter here, but in my conclusion, I'll go back to some of the motivation for this project. I'll bring up U.S. Public Law 103-150, which in summary is it's called the Apology Resolution from the United States government to Hawaii. It basically says that, prior to the first arrival of the Europeans, that the Native Hawaiian people lived in highly organized and self-sufficient social systems, and that the Native Hawaiian people are determined to preserve and develop their cultural identities for future generations. And like I said, I've seen this firsthand with some of my friends that have farms like in Waikane and Kahana. And this issue, the UXO issue, is directly in the way of that because they're not able to access a lot of their lands. So with that, I end this with a request for collaboration, assistance, or helpful ideas to help solve the specific issue of UXO detection in homogeneous high iron content soil and discriminating them from high iron content large rocks. And with that, I open the floor to questions and comments.
Thank you very much, Andrew. Great. I don't see any questions that have come in yet, but certainly from my perspective, with those high concentrations of magnetite in the rock structures there, what are you finding that they are in sort of concentrations of particular lava flows, or has there been quite a lot of geomorphology processes later that has distributed them more widely?
Typically what we're seeing is that they're homogeneously scattered kind of all over. There'll be pits of large rocks that they'll find deep in the ground, but really it's hard to tell where those pits will be. They did start with lava flows, so I think that might be what you mean by like a geological event that spreads it out, but we haven't been able to tell if we can find specific locations where they are at.
Yeah, because it's quite interesting that obviously these islands have built up over millennia and from subsequent events, and I would have thought that there would be some sort of pattern to it, but if it's homogeneous, then it's almost like the eruption event itself is always generating the same type of material from the concentration of the magnetite within the rest of the silica material.
Yes, I think that's what we're seeing. So there is an active volcano still on the Big Island, and I think that the lava that comes out of the volcano it's highly ferrous, and so it just generates these rocks that the rocks break down into the soil over time to make the soil high in iron, but before they break down, you still have these rocks. At least that's what I think we've seen.
Right.
And for our audience, I did see, it looked like 2 hands raised and then they went back down. If you do have a question here for Andrew, please raise your hand again. Okay, there it is. Garrett, it looks like. If we can unmute Garrett's phone, looks like he has a question.
Go ahead, Garrett.
Hey, can you hear me?
We can hear you now,
Yes.
Garrett.
There we go. Sorry about that.
Oh, no problem.
Yeah. My question was in the Q&A, but I guess they're not popping up. I was going to ask, in the Waikoloa maneuver area, what percentage of the UXO is surface and subsurface?
So let me go back to this slide. Over like 90% are subsurface, what they found. There are very few are on the surface. In fact, the only ones that stick out to me that are on the surface were the grenades that they found at the elementary school.
All right, understood. Thank you.
I do have a question here now from Michael Maxon. How are you building your models for the simulated data? Are these based off of physics? Are you starting with Maxwell, or are you starting with an unknown program like EMCOS?
That's a good question. That's kind of the reason why we're in this conference. We're only 6 months into this project. We haven't really made those decisions yet. I think we want to start with an EM-based model, but I don't think we're really sure. I know that my advisor, Dr. Wayne Chiroma, is in the chat. If he has an answer to that, maybe he can raise his hand, but I don't know if he knows either. Maybe he does. So yeah, that's one of the reasons why we're here, is to find, get ideas for where you can start.
Hopefully, Michael and yourself can touch base a bit more on that. I think we're close to the break time now, I believe, Bob. Is that correct?
Yes. So here's what we're going to do for the break. We have a break scheduled for 10 minutes, and then we're going to extend that and go for a 15-minute break, so that we'll come back in 15 minutes from now, so we can have 5 minutes for some of the questions from the previous talks, and then we'll dive into Chris Price's presentation. Okay, so we'll do the markdown.
See you all in 15 minutes.
Yep.
Well, I've got another question for Mike, if he's back on.
Yeah.
Hi. So I just wondered if you could provide a bit more details about your experiences using the SLAM positioning system, and any pitfalls that you might have come across, or any particular successes.
The pitfalls, I mean, not many. It's not many. It's just an excellent system. I think that there was some hesitation or nervousness, because it's a new technology, and there are a lot of things going on with it. But once we embraced it as a geophysical tool kind of thing, that it's just software and positioning. We absolutely love it. It's easy to use. Once you set up that cloud, so again, real quickly, you essentially set up a cloud, so you have this big local reference system, and then you just tie it into real world coordinates, and you can make really big areas, and then the sensor just goes over the sensor head, or goes on top of the geophysical sensor, and away you go. And the positioning accuracy, I mean, it's below 10 centimeters. It really is. It's super accurate, and we're looking for applications outside of just mapping in wooded areas, but the ability to potentially leapfrog, do transects, long linear miles, urban areas where your GPS is in and out. Just set up a cloud, it will bounce off those buildings and reference itself, and away you go. So not just munitions response geophysics, but anybody out there doing utilities, where you do want that kind of positional accuracy, the SLAM system is highly recommended.
Thank you very much. So yeah, is Christopher back with us now?
Yeah, can you hear me okay?
Yes, he is. Yep, we can see and hear you, Chris.
Great. So we just had a question regarding the graph you showed with the
My fault. I was talking to Chris Price.
Oh, sorry. Okay.
Yeah.
Sorry, Chris.
I'll tell you what, we're gonna hold off Chris Virgil's questions till the end of the session here, just to keep us on schedule. And I'm gonna go ahead and introduce Chris Price from Oklahoma State University. Chris is going to talk to us today about data gaps for the ordnance recycling community of interest to achieve AI/ML powered decision-making tools. And also one more note to our audience for questions. Once again, if you have questions for the speaker, please put them in the Q&A chat section, and also put the speaker's first name at the beginning of your question, so we know who to go back to with that. And we will cover all the questions that are in the Q&A chat. All right, Chris, the floor is yours, sir.
Okay, thanks a lot for that intro. Yeah, so I think for my presentation, I'm not really going to solve any problems for anyone. I'm really just asking for some help on behalf of a subset of the ordnance community, folks that are involved in explosive harvesting. So with that, I'll pull up the PowerPoint, and hopefully that's working. Is that showing up right on the? Okay, great. Yeah, so I'm going to just do a quick process of overview of explosive harvesting, what that entails, in case anyone is not familiar. And then we'll go into the data gaps after that, and how we can really use your help from the geophysical detection community. And then kind of like some suggestions and kind of prompt for discussion on the way forward to use some decision-making tools based on this new data that we'd be able to get from novel and improved existing sensing techniques. So I laid this out as a flow chart, really just as a basic overview of how explosive harvesting works. And really for this conference, we're focused on the first three steps, right? So I'll brush through the back end of it, but these first three are probably of most interest to this audience. Okay, so when I'm talking about localizing, it really can be one of two scenarios. One, the scenario that most of the presentations this week have been about, where you're looking for buried or surfaced ordnance on land, or in some cases even underwater. Because I'm a Navy EOD guy, so I care about the water a bit, and ordnance that's on the bottom down there. Yeah, so from localization. It can be from platforms like Green Sea's autonomous unmanned ground vehicle. It could be one of the many UAS that have been briefed throughout this week, or underwater systems such as marine magnetics. Appreciate this product from Doug for that awesome graphic that shows the value of magnetometry underwater. But the second scenario can also be stockpiled munitions or some other area where ordnance is stored, and we need to go through a large area of munitions that are abandoned or just stored and need to be remediated for one reason or another. And we need to hash out which ones are suitable for harvesting and which ones just need to get disposed of one way or the other. So that's localization in a nutshell, relevant to harvesting. Then identification. This is probably where we need, between this and a characterization, where we need the most help on explosive harvesting and data gaps that geophysical detection can aid with. So here we need to identify what kind of ordnance is it, what kind of hazards are associated with it, what are the fusing, has it been fired or is it just abandoned or dropped, right? And so additional granularity other than, yeah, there's something metallic there. That's what we're going for in this phase. And then same thing on the right there, we want to identify, so because sometimes when ordnance is stored in crates or in magazines, it's not always accurate to what the labels say. We see that in a lot of foreign countries where storage practices are non-ideal, we'll say. And so a way to remotely measure with some standoff without having to break into containers and crates and everything to confirm the identity of that ordnance would be super helpful. And then for characterization, this is where we want even greater granularity on the condition of that ordnance and characterize its hazards and the type of ordnance itself. So we're interested in the orientation of it. We're interested in, again, whether it's been fused or whether it's been armed and unarmed, those kinds of conditions. And even down to what kind of metal is it, what kind of chemical fill is inside of it. So these details help us with deciding whether something is worth pursuing for harvesting, or again, if it just needs to be blown in place or transported to a local disposal area. And then once we know as much as we can about the ordnance from remote or up close investigation and reconnaissance, then we go into either the decision to either remove it and transport it, remove and dispose of right there, or blow in place, or even render safe it, and then have the ability to move it if needed. This was just some ERW in Solomon Islands, mainly from Guadalcanal back in World War II, where they had to, there was a lot of environmental rules at a site that ordnance was found, and also some historical considerations like burial grounds and things. And so we had to move it before we could harvest and cut open the ordnance. And then the interesting part for a lot of folks is really the accessing, harvesting, and reconstitution into a new explosive tool for follow-on EOD procedures. So in terms of accessing, on the left there, we have from Golden West Humanitarian Foundation the result of a cutting system that they use remotely to be able to cut into it and then access the explosive fill. And then they can cast out and pour into new blocks to make explosive countercharges. And it's a really cost-efficient method to do humanitarian demining, and they do a lot of this in the Asia Pacific that I'm familiar with, and then also around the world. And NGOs are moving to this process because of the cost efficiency. On the military side, you see on the right there, that was from a recent exercise where we worked with Navy EOD, worked with Marine Corps EOD, and Japanese Ground Self-Defense Force EOD folks. And we just show some of the processes that you use to get to reconstituting ordnance. And this would be double boiling, grinding depending on the sensitivity, and then you can cast it out into shapes. It's even effective for shape charge utilization. There's just more testing that we need to do to get after that problem. Okay, so now we kind of have a baseline understanding of what it takes to go from ordnance in the dirt or a magazine all the way to accessing it, cutting it open, pouring it out, and making a new charge for follow-on operations. Here's some of the gaps. I touched on some of these in the last few slides, but there's a few others that we didn't. So for localization, precise burial depth is one area that we could really help get some more fidelity on. So that comes into a number of factors. One is how hard is it to get to the ordnance item? That's the most obvious one, but also how much pressure has the ordnance undergone, and that burial depth can help us better of how much pressure is been placed onto that ordnance item, but also how difficult is it going to be to excavate the area surrounding and do a procedures or remove the item. And for identification, like I said, this is probably where we could use the most help. If there was a way to really, probably with supervised learning and those kinds of things, get down to ordnance type, but then even greater fidelity from the geophysical methods discussed this week. Precise dimensions and orientation is really huge. And again, knowing what kind of material it is it steel, is it alloy, is it aluminum charge, that can help narrow down what kind of charge it is too, down to the specific nomenclature possibly. Chemical composition, this sounds like a hard one. I've heard of, there's been some experimentation with, chemical sniffing robots and things like that. And it has had some success, but you have to get very close, and it has to be one of just a couple specific compositions with a strong library to back it up. So that would be another large area of future research is chemical composition detection with standoff. Maybe that's through sensing the dialect risk, and also how useful that charge would be down the line if we were to reconstitute it. Age, in terms of how old the ordnance item is, or even just knowing how long it's been down there, that would help with risk assessment and the utility of the item. And then for underwater, also we want to know about the water itself, temperature, salinity, things like that, just for mission planning, and also depth, and again, material conditions of the seabed around it. And then for characterization, if there's ways to extrapolate the fuse condition of the ordnance item, that gets to what we have to do next in the process, and better understanding the risk we're getting into before proceeding. Identifying if there is propellant and what kind of it and how much of it has been burned, if any, that would be useful. And then from a materials perspective, understanding the corrosion and abrasion, because if there's a lot of corrosion and it's already seeping out explosive fill, we see that from underwater ordnance and back from World War I, World War II, when it gets past roughly the 80 to 100 year mark, then it's probably going to be contaminated with salt water for underwater, or even groundwater and other externalities from ground surface ordnance. From kind of like an ops research perspective, the middle and the right side of things gets into cost functions from logistics, regulation, compliance. Like, is it worth going through the steps for it? So that's not really relevant as much for the geophysical side of things, but these are data gaps that we need to compile, and as a explosive harvesting community, need to do better at cataloging, so that way we can make decisions on future operations. And then same thing for the last three steps. How feasible is it to access? Some of that is derived from these other blocks here on the left of the screen, and then and same thing with risk of high and low order detonation probabilities. We're going to know that if we know if it's been there a while, if it's undergone pressure, if it's undergone increased pressure recently, those kinds of things. And then volume of energetic material that would come from net explosive weight and precise dimensions, and the quality of explosive fill is from knowing the chemical composition, but also if the ordnance casing has corroded at all. All right. And then for way forward, basically all these data gaps that I just went through can help serve as data inputs to fuzzy logic controllers, essentially, where none of these operations are a 0 or 1, not a binary decision as to whether an ordnance item is worth harvesting. It always comes down to some kind of subjective analysis of the situation. All right. Okay, so on one side of these scenarios, we have ideal situations where we have large ordnance items, heavily aggregated, ideally that they haven't been fired, right? So it's safe. They're shallow buried, if at all, or even on the surface, sitting proud. Unlikely to high order. The main charge is feasible to harvest, and it's not in a remote location that's a pain to get gear out to. On the other side of it, it's the opposite of all those things. Inferior charge for harvesting, remote location, and you have a bunch of armed grenades scattered about a large area. So what we're really looking to have decision-making tools for is that gray space in between, when it's not obvious, like, yeah, it's a 500-pound bomb that's not going to go off, but and it's not a grenade that's super risky to even look at. So there's references you guys can look at afterward. Pending any questions, that's all I have for this group. Thanks for your attention and time and the opportunity to talk about this topic.
Thanks very much. Very interesting. Don't see any questions here at the moment.
Oh, it's so much easier when you do take the mic off. Okay, I'm back with you. All right. So we do have about 3 minutes that we could take one of the questions, whether it's for Chris or any of the previous speakers, which I know we do have at least 2 here for the earlier talks.
Brian Brunetti has just posted a question. Which part do you think is most subjective, Chris?
The most subjective is probably in the ops research section, where how expensive something is. That's all depending on the organization that you're coming from and the kind of access you have to that operating area. But on the left side of that flow chart, I would say probably fuse details, and the condition of that fuse. That to me sounds like it's going to be the hardest to determine from remote sensing means.
And Ted has got a question here. How do you think you're going to do the chemical analysis while in detection mode?
Yeah, that's a really good question. It's almost like I think you're only going to be able to get chemical analysis done if you do have seepage out of the container due to cracks in the casing, in which case you probably don't want to harvest it. So that's kind of a one of those wicked problems that we're dealing with. If you can at least get down to dimension and material, then you can narrow down from a library of ordnance. We think it's probably filled with RDX, TNT, Comp B kind of compositions based on our library, or if there's a way to sense even the nomenclature on there. So in the underwater world, when we have synthetic aperture sonar, sometimes if you have a mine or a torpedo sitting proud on the bottom, you're able to make out the imprinted nomenclature of the ordnance, and from there you can pull up from whatever library or database you have, oh, it's this fill. So you're probably going to get it secondarily, not directly from a chemical analysis means. I don't think we're putting gas chromatography systems on UAS anytime soon.
All right, well, thank you, Chris. All right, we're going to go to our next speaker again. And Chris, we're hoping you can stick around till the end here in case we get some more questions on your talk. And next speaker, if I pronounce this right, Jorge Lopez Alves from University of British Columbia. And your talks on using convolution neural networks to classify UXO with multi-component electromagnetic induction data. All right, sir, the talk is yours.
Thank you very much, Bob. Thanks for the intro. Can you hear me okay? Okay, thanks a lot.
We are
okay.
Good, sir.
Yeah, so I will present just basically what I did as a postdoc at the University of British Columbia, and we collaborated also with people in Black Dust Geophysics. And it's just, we were trying to design a convolutional neural network to classify UXO. And we were just dealing with multi-component electromagnetic data. If you were here for Mike Anderson's talk, it's just basically the AGC systems, the Advanced Geophysical Classification Systems. Was just the neural network we designed is basically for that kind of system. So a very quick overview on time domain EM response of the UXO. We have a transmitter here where the electrical current is on. Then we suddenly shut it down, and that induces a dipole moment in our UXO, and that dipole moment decays in time, and it has an associated secondary magnetic field, and that is what we record in the receiver. And the equations or the model that is usually used to model the response of the UXO is that of the kind of assuming that we have 3 orthogonal dipoles in the center of the UXO. And depending on the dimensions of the UXO, we have the electromagnetic decay that is slower in time for the longest axis. And for the UXO, since it's an axially symmetric object, we have the transverse directions have a faster decay in time. And we usually parameterize this with what we call polarizability. So the L's here are also known as polarizabilities. L1 is the largest, and L2 and L3 should be coincident for UXO. And if we have any other piece of metal that doesn't have that axial symmetry, we will have that L2 and L3 are not coincident. Again, this is just the equations. The important thing to notice here is that we require the position of the UXO, its orientation, and also what we call the polarizability tensor that we have here. So the traditional approach to classify these objects is to use inversion. So we basically get the position, the orientation of the UXO and its polarizability tensor, and then we simply use only the polarizability tensor and compare it with a set of ordnance objects that are already recorded in a library. And if we find that there's a match with the library, we just basically assign the label to that object. So the kind of system that we will be working with is an underwater system. The data that we used to test our method was this underwater system. Is the ultra-thermophore system. It has 4 transmitters here in yellow, 12 receivers, each here shown in black. Each of them is recording 3 components and 27 time channels. And the system is designed to go under the water and hover approximately 1 meter above the sea bottom. So the data of this system, if we were to plot it, we will get something that looks like this. This is the layout of the system. We have the along track, the cross track dimension. The system is moving in this direction. And in the lower part, I'm just showing the data that will be recorded only by the first receiver shown here. And each of the transmitters is firing sequentially. So each of the different colors is just basically the firing of each of these transmitters. And here I'm just highlighting in this orange box the first cycle of the transmitters. And then the lower part, the corresponding box is just showing the data points associated, or basically the soundings associated with this first cycle. And you notice that we have a UXO here. So when the system starts to get closer to UXO, we see a significant response, a significant electromagnetic response from this kind of system. So this is just a quick review. If we move to the next position or the next cycle for the transmitters, it would look, it will be just basically these second points and so on. Well, but the thing that we propose here is, instead of using inversion as an intermediate step to classify, can we classify directly from electromagnetic data? And the way we propose to do it is using convolutional neural networks. And these are very, very useful when we have the kind of data that I showed you in the previous slide, where we expect to have some kind of spatial and temporal correlation in the data. And the way the CNNs take that into account is just basically, if our input looks like this, it was just basically processed like a central pixel and all its neighbors and produce a single output. So in this way, this kind of model, these kind of functions allow us to take that kind of correlation in the data implicitly in the architecture of the model. And another nice thing about the EM classification problem for using this kind of CNN is that we have, although we do not have like the tens of thousands of examples from field data that we already have labeled objects with field data. The nice thing is that we have this library of ordnance objects, and we can use that library to generate synthetic data using the dipole motor that I showed you before. And since it's a very fast simulation, this dipole response, we can get hundreds of thousands of examples in a relatively small amount of time. And we can use that synthetic data to train our CNN and just basically use that trained CNN to classify data on the field. So again, very quick overview of CNNs. The way we're using it is a supervised classification problem where we are provided data with labels, and we need to construct a function, in this case, the network that outputs labels given input data. So the classical example is to take our input is an image. So the image has a certain width and height, and it also has 3 RGB channels, right? And the neural network is just basically a function or a composition of functions that takes that input X and outputs S. And each of the layers is just basically, in a simplified manner, is just a matrix multiplication followed by what we call a nonlinear activation function. And the weights of each of these matrices can be represented with this parameter theta here. And basically what we're trying to do is, if we show many examples of labeled images, and I have to make a note here that we're considering what we call an image segmentation problem. So we're not producing a single label per image, but we're also labeling each of the pixels of the image. So that's called image segmentation. So once we show the neural network during training many of these segmented images, the neural network will estimate the parameters theta of the neural network, and then once it's trained, the neural network will be able to output something that would look like this. And even for images that it didn't see during training, it should be correctly segmenting the images. So now the question is, how do we translate these things to the UXO classification problem? Now our input, of course, now looks like this. So the way we propose is just to structure our data in a certain way as to kind of exploit this image-like structure that it has. It has correlation in both in space and time, our data. So NX, for example, will be the number of positions in a spatial window. These systems generally acquire data per line. So we will just take a certain number of transmitter cycles, and that will be that we will put in this first spatial dimension. And in the cross-track dimension, we will simply consider the number of receiver cubes. Since each of these receiver cubes is set up in a way that it has a different cross-track position, we will also take that into account. And then we have a third dimension where we just put the time channels. So it's kind of a structure. Instead of being an image, now the input is a 3-dimensional input. And then analogous to the RGB channels, we're considering data, kind of the dimension of data where we expect to find independent information. So that will be related to each of the transmitters. And also 3 is here for each of the components of the receivers. And then I won't get into too much detail of the architecture, but we're considering first 3D convolutions, but later on we restructure our input and we just consider 2D convolutions. And this is just because we want to preserve only the spatial dimensions in order to produce a 2-dimensional classification map. And yeah, so that's why we choose this certain way. Notice that the NX and NRX are preserved in our output S. Now here we have, instead of the channels, input channels, we have the number of classes in our output. And from that, we can also produce class probabilities. And if we simply assign the label for the maximum probability, we'll end up with something that looks like this. So it's very similar to what we have for the previous, for the image situation. But, and now the question is, how do we obtain these kind of labeled, what we call mask labels or segmented images? We follow a relatively straightforward approach where we consider the magnitude for each of the transmitters. We basically arrange our data in this way and consider only one of the time channels. We normalize by the maximum amplitude, add them up, define a threshold. Since data are normalized by the maximum amplitude, we can use the same threshold for all the samples that we generate. And then we, with that threshold, we simply crop, crop above that threshold and assign everything, all the pixels here in this small image that are above that threshold. We will assign the particular type of object that was used to generate this synthetic data. So in this case, for example, the pixels here in pink are for a clutter object. We also know the position of each of the receivers, so we can send back to the footprint of the system and obtain something that looks like this. So yeah, so now showing the application to a line of data. As I told you before, the system, this kind of system usually acquire data line by line. So our input features will be created by using a sliding window. So these are different positions of our system, and just system is moving from left to right, and we have a UXO at this point. So the first sliding window will be considering only these positions shown in red. This is the sliding window. And the neural network output for this first window will be all blue, because blue is giving us the background, and since it's far from the UXO object. But then if we simply slide that window and get close to the UXO, we start to see how it's changing the color. And basically this orange color is giving us a certain type of UXO. If we apply this to the full acquisition line, we will end up with something that looks like this. Again, each different color is a different UXO. Now, as I told you before, we need to use synthetic data to train our neural network. The way we do it is we consider 7 different classes. Here you have to adjust of the number of classes, UXO classes that you expect to find on the field. And then you simply randomly assign the target, the location. The location, we're considering basically this red box here below this sliding window that I told you before. We also randomly assign the orientation, so we were able to classify objects that are pointing upwards or lying flat on the subsurface. Sorry, and we consider 400,000 simulations to train our neural network. So again, because we're considering the dipole response model, that's relatively fast, and we can manage to do it. Important parts here are how we design the clutter object and how do we assign the noise. Well, of course, we have to also assign some noise to our synthetic data that is representative of what we have on the field. The clutter design is just using this kind of equation where we have 3 different parameters, K, beta, and gamma. And we simply take a few objects from the ordnance library, estimate its 3 parameters, and then we consider like a 9-dimensional parameter space, and we simply fill the rest of this parameter space with points. And from that points, we can recreate the polarizability curves that will be for the clutter objects. And we consider those as clutter objects during training of our CNN. Just quickly to get to the application, to the field data, we consider data that was acquired in sequence-based test site for 2022. Here's what they call the calibration grid. So we have objects more or less placed regularly. And we have 7 acquisition lines. So the system goes this way, returns, and so on. And the current workflow requires that we remove the seawater response, since the seawater and sediments are very conductive, we have to remove that response first, but we already pre-processed for that. The data I'm showing here, the upper part, is already pre-processed for that. Then we also have some standard ISO objects that are not UXO per se, but are like more like pipes, but they have similar sizes. So we would expect our CNN, even if it was not trained seeing that particular kind of objects, we expect our CNN to actually classify as to with the closest object in terms of size. For example, the medium ISO, maybe it's classified as a 81 millimeter. As I told you before, one very important step is that our noise is representative. The noise we add to the synthetic data is very representative of what we actually have on the field. So the way we do it is we use another CNN, but this one is just to tell what's a background and what's an object. So basically here, everything that's in orange are both UXO and clutter objects. And we simply take a zone around that, all the anomalies detected, and we crop that zone out. And what what we are left with, we use to estimate that spatially correlated noise. We add that new noise to a new training data set, and we use that training data set to train a neural network. And once trained, we are able to produce the classification map that looks like this. So basically here, every different blob every blob is an object that was classified by our CNN. And you notice that some of the objects have like a little bit of mixing of labels. And so in order to produce a single label per object, we perform some kind of voting scheme. And that voting scheme will, if we apply that voting scheme, and we also take like the center of mass of each of these blobs, we will end up with something that looks like this. So the ground truth is in black, and the predicted label is in green. So a couple of things to notice here is that we discriminated the clutter. We did not miss any UXO. Even the smallest ones, 60 millimeter, 40 millimeter, were correctly classified. And we also, what we expected, the 81, the medium ISO were consistently classified as the closest object in terms of size, 81 millimeter, and the large ISO was consistently classified as 105 millimeter. A key points is that we use this image segmentation architecture that was very important to produce high resolution classification maps. The clutter design and the correlated noise are very important. If we didn't design the clutter correctly, we would get a lot of false positives. And the correlated noise was important to increase the classification accuracy. Limitations so far are that we haven't trained to handle multiple objects in the same window, basically they call sometimes the multi-target scenario. The objects that we use to generate synthetic data should be close to the objects on the field. So the list of objects that we expect to find should be consistent with what you have on the field. Otherwise, you will get inaccurate results. And future work will be to explore this multi-target scenario, consider maybe some modifications to our architecture. And in the end, we do not mean to propose this approach to replace the traditional approach. It's more like trying to combine with it and exploiting the pros and cons of each of these two worlds, and maybe come up with some hybrid approach that is optimal in both senses. So with this, I will conclude my presentation, and I will thank you for your attention.
Thank you very much, York. That was extremely interesting. I do have a question for you. You showed a chart which had your cluster points for the different munitions, and they were color coded, then surrounded by lots of points which classified your clutter.
Yeah, this one.
Could you? Are you considering each of those points as a bin, sort of a bin size? And my second part of the question is the cluster that you get for a particular munition type. Does its radius determine its sort of confidence level? So if you're nearer the circumference of that cluster, are you less confident than if you're in the center of that cluster?
Yeah, that's a very interesting question. Yeah, I think I failed to mention that here I'm just basically estimating for a single of the objects that I expect to find in the field. I get only a single point, and then I'm adding like a Gaussian distribution around it just to increase like sort of kind of reproduce the diversity that we will expect to see from some objects. But kind of I didn't do this part like very rigorously. It was just to try to account a little bit for slight variations that may occur even when you don't have a perfect kind of UXO object. So yeah, that was more like I test different values for this this Gaussian distribution that I'm adding, and this one was working. Yeah.
So you could potentially have the radius of those clutter of the target areas to be larger or smaller depending on what you rate the quality of your data.
Yeah, I think we can adjust by trying different depending on the quality of the data, that we can adjust that. Yeah, that will be one way. There are different ways to actually kind of add more kind of that quality of the data, but that would be one approach. Yes.
All right.
Thank you,
Well,
Al.
thank you, sir. That
Thank you.
was an excellent talk. I want to borrow some of your slides for mentoring our younger geophysicists as they come on board.
Sure.
Please stay around because we'll have more questions, I'm sure, on that talk after the next speaker. So
Sure, thanks.
with that, if I can introduce the next speaker, Yuquin Huang from the University of Houston, to talk on deep learning, enhanced GPR, full waveform inversion.
Thank you. Yeah, thank you for the introduction. And hello, everyone. My name is Yuqin Huang. I'm from the University of Houston, and I work as a faculty in the Department of Information Science Technology. And today, my presentation is about using deep learning to enhance the GPR full waveform inversion. We know that the GPR can provide us very valuable information about the composition, the depth, the geometry of objects, and structures beneath the surface. And we all know that the conventional GPR involves the manual data collection performed by human operators, and also by the UAV or drone-based GPR system, which have gained a lot of attention recently. And actually, we can tell from our conference, right? But whether the data collection relies on human operators or the machine-assisted approaches, the core of GPR resides in the signal processing and imaging. The precision and the reliability of GPR signal processing and imaging algorithms are of great importance because any deficiencies or inaccuracies in these methods will significantly impact the quality of the subsurface images. So why do we lean towards using the full waveform inversion? First, let's review three primary imaging methods. So first, we have the traditional GPR tomography method based on the ray theory, like the ray tracing or the attenuation tomography. But this method only uses a very small portion of the signal data, and it struggles with smaller anomalies and also the low velocity zones because the signals may just bypass these significant features. And also we have the migration method, right? And migration is a very popular and widely used data processing technique in GPR service to improve the accuracy and the spatial resolution of the subsurface imaging. GPR migration works by repositioning the scattered radar signals to their correct locations. Despite its benefits, the migration struggles with complex subsurface structures, and also it does not reveal the electromagnetic properties. Therefore, both the migration method and the ray theory-based method, they do not answer the fundamental question of what lies beneath the subsurface. And in fact, this brings us to the full waveform inversion, or we call it FWI. The FWI is a more advanced method that aims at obtaining a highly detailed and accurate model of the subsurface EM properties. It uses the full waveform matching to accurately to create a highly accurate subsurface model. And of course, this method incurs much higher computational costs. But because the FWI can harness the complete waveform inversion, it can achieve the sub-wavelength level resolution, could be 1/2 or 1/3 wavelengths. Plus, the FWI output is the distribution of the subsurface EM properties. So it's promising to answer the question of what really lies beneath the subsurface. So that's why we are focusing our efforts on FWI. It really helps us understand what's underneath. And this page here is a typical inversion workflow of FWI. Basically, it is an iterative process. It starts with an initial model and then call for forward modeling to get the predicted data. Next, by comparing this predicted data with the observed data, we use a kind of algorithm to update the model, and then use this updated model as the new input to the forward modeling, and then run this loop again and again until the misfit between the predicted data and the observed data is small enough. And here is a group of comparison between the results of FK migration and the FWI using this synthetic 3D GPR model with two permittivity anomalies. And the first column, these images are of the raw GPR data, and this second is the FK migration results. And the third column is the FWI method results. And also the top row here, it shows the image slides with a fixed X coordinate. So basically the slide is cut along this direction. And the bottom row is the slides with a fixed Y coordinate. So it's cut along this direction. So by comparing these migration results with the FWI results, we can see that the migration method only relocates the radar waveform, and it is unable to characterize the properties distribution. And also look at here, it fails to distinguish different objects' locations when they are close enough, right? But in contrast, the FWI can not only distinguish the object's locations accurately, but also provide us a very high resolution information about its size and its permittivity distribution. So this also means that the FWI enables the buried objects classification. It can tell whether the object is metal or plastic or anything else. Despite these advantages of FWI, there are several bottlenecks hindering its widespread application in practice. And one major challenge is the so-called cycle skipping issue. And this issue is primarily stemmed from the absence of the low frequency signals. So let me explain by using this figure here. Look at this figure. So this is a schematic. It shows the roles that the low frequency signals and the high frequency signals play in FWI. And let's look at this red dotted line here. And this line is the cost function by the low frequency signal. So this low frequency signal exhibits a weak nonlinearity and yields a valuable initial model. Let's say, like, for example, this red dot here. And this initial model is close to the true solution, which is this dot, this dark blue dot here. And on the other hand, let's look at this blue solid line here. And this is for the cost function for the high frequency data. We can see that the high frequency data introduces high nonlinearity, and the inversion is prone to getting trapped into a local minimum when the initial model is distant from the true solution. For example, when the initial model is indicated like in this green dotted line, then it is very likely that it will get trapped into this local minimum. And essentially, the GPR FWI itself is a highly nonlinear problem, which means that it is very easy to get trapped in the local minima during the inversion process. So a good practice is to use the multi-frequency approach. It means that we can start with the low frequency data and then use the solution from the low frequency inversion as a robust prior for the subsequent higher frequency inversion. So in this way, the cycle skipping issue can be avoided. However, in reality, in current GPR technology, obtaining the reliable low-frequency signals, let's say like 10 megahertz. Okay, so these low-frequency signals are below this part is often challenging due to the limitations in the antenna bandwidth, the low signal-to-noise ratios, and also the design of data acquisition filters. So when FWI is applied to this band-limited data with the missing low frequencies, it frequently will lead to the subsurface image with pronounced artifacts and inaccurate EM property estimation, and eventually high false alarm detection. So the figure here is a synthetic GPR model with two permittivity anomalies. So this is Lagrange choose, and the middle image, it shows the GPR full waveform image with both the low and the high frequency signals, and the third image shows the GPR FWI image with high or a high frequency data only. And from this comparison, we can clearly see that the cycle skipping issue, and we also can understand the importance of recovering the high quality, low frequency signal for GPR FWI. And this is the existing workflow of FWI with the high frequency GPR data only. So here we just put the high frequency GPR data into this full FWI module, and also give it an initial model, and finally get the inversion results. So again, because the low frequency components in observations are noisy and unreliable, when we only use this high frequency FWI, it may cause the cycle skipping problem, and the inversion results will not be correct. To solve this problem, we propose deep learning enhanced GPR FWI workflow shown in this figure here. So what we actually do here is to develop and implement a deep neural network for learning the GPR low frequency information, and then use both the observed or measured high frequency data and the machine learned low frequency data for inversion. And more specifically, we use the machine learned low frequency predictions to generate to run the FWI and generate a good and robust model, which later will be served as the initial model for the high frequency FWI. And we think that in this way, the predicted low frequency data can guide the solution to avoid the local minima, and thus we can obtain a global optimized solution by using this new workflow. And here are some results from a group of synthetic cases. And the top row is for the first case. Here we use 4 transmitters and 8 receivers to perform the GPR FWI. And here the data amount is very small. And the second case is for a 2D cross-hole GPR case. For both these cases, we use the 600 MHz as high-frequency data, and then we predict the 100 MHz and the 300 MHz for lower frequency GPR data. So the first column is the ground truth, and the second column is the FWI with the synthetic full bandwidth data, including both the low frequency and the high frequency data. And then the third column shows the image based on the high frequency data only. And the last column is the FWI results with the high frequency data and the deep learning predicted low frequency data. And this preliminary study demonstrates that the feasibility of our proposed scheme in reconstructing the low frequency GPR signals and achieving the performance similar to that of the FWI with the full bandwidth data. So here's the conclusion. In this work, we propose a machine learning enhanced method for GPR FWI. And the machine learning approach is used for reconstructing the missing low frequency information of the observations. And our method has been validated by the synthetic cases. And our next step is to conduct tests by using the field data. Yeah, so that's all for my presentation. Thank you very much for listening. And I'm happy to take any questions.
Thank you very much. That was great. I've got a quick question about your previous slide with the XY distribution case 1. Were you transmitting on one of those nodes and receiving on all the others, or was it just a common offset pair?
So we run the simulation just one source by one source. For example, for this one source, we have 8 receivers, and the next source we have 8 receivers.
So in a practical terms, with general GPR systems that are a constant offset, you would have to do some resorting of the data.
Right, but here we don't have to do the resorting. As long as we have the location of the source and the receiver. Mm-hmm. So it's different from like the migration. Yeah.
So yeah, with regards to your lower frequency, in these examples, you were using 100 megahertz and 300 megahertz as the lower frequency side of your model.
Yeah.
But previously you were talking about going down to sort of 10 megahertz.
Yes, but right.
What's your cutoff? What's that sort of frequency cutoff? Is there any particular cases where you have to go down even lower to that 10 megahertz, or will 100 megahertz be reasonably sufficient overall with your predictions?
That's a great question. So actually, when we do the synthetic simulation, the tests, we didn't know about in the real world how low the low frequency data is missing. So we do this kind of simulation first, and then we did lots of literature review, and we found that like it is more likely that the 10 megahertz below this 10 megahertz area, this range is more likely be the missing frequency, but we didn't get time to redo the simulation, but we will do that because we are collecting the field data. So the field data it will be more like for the realistic application. So did I answer your question?
Yes, you did. Yes, yeah.
Thank you.
Does anyone else have any other questions? I don't see any in the Q&A section at the moment. If anyone does, you could raise your hand and then we can unmute you. Oh, here we go. One here. Brian's got one. Is there a distance/depth limitation with this method?
Well, it really depends on the material of the objects or the soil condition, right? If the soil is very wet and we know that the EM wave will get the attenuation is large, so the detection range or the depths will be much smaller. So it really depends on the EM properties of the detection range, the detection area.
Is there any way in your modeling to characterize where that sort of depth of detection tolerance comes in? So through the four waveform inversion method that you're using, is there a way of saying, well, actually, our depth of detection limit is X depth because of the results you're seeing?
Yes, we can do this kind of analysis by running a bunch of simulations, setting in different background properties and different inversion range. We can do that by run a series of tests or the simulations. Yes.
Does that significantly increase the computation time?
So we use the GPU. So it depends on the computational resource. Basically, so right now, yes, if we use the rigorous forward modeling, yes, it is. But right now we are working on using a deep learning method to generate like a surrogate of the forward modeling module. So ideally, the computational cost will be greatly reduced if we complete this part.
Fantastic, thank you.
You're welcome.
And we do have another question from Johan's. We can unmute Johan's speaker or microphone.
Okay. Now I'm unmuted. Yeah. I'm sorry. I think I have a general question or general problem of understanding. If I get you right, I think the problem you are addressing, the cycle skipping, yes, arises from the fact there is a difference between the model waveform predicted by a certain velocity model and the observed waveform. Is this correct?
Yeah. So because the low frequency, it has the low frequency signal, it has the very much lower non-linearity, and
okay.
Yes. So actually, so here, yeah, we use the velocity here, but actually we use the parameters because we use this we applied this idea to the seismic data processing. So that's why we use the V here, right here. Yeah. Mm-hmm. Yeah, I didn't aware of that. Thanks for letting me know.
And would it be possible by improving the model of the speed of the electromagnetic wave in the subsurface to adjust it accordingly?
Could you please say it again? I didn't quite understand it.
A delay or a difference between the observed and the picked waveform of your GPR signal, the difference maybe can be minimized by adjusting the velocity model in the subsurface.
Yeah, so this is more likely the what the Ray theory based imaging method do, right?
And last question: what phase shift between the predicted and the observed waveform do you allow in your model?
So you mean the may I have?
Yeah, you use a certain velocity model in the subsurface to explain your GPR signal and the waveform, and the problem, as far as I can understand, is that there's a cycle problem or a cycle skipping problem.
Yes.
So the phase between your predicted and your observed is not zero, right? And what accuracy with regard to the phase do you allow to accept the model?
So usually it will be like more than half wavelength difference.
Okay.
Yes.
Yeah. All right. Interesting. Thank you.
You're welcome.
Hey, Matt, why don't we go to the Q&As and go all the way back to the first speaker for Christopher Virgil. You will notice there's at least one more question that will be coming up for you in the Q&A, so you can take a look at that and get prepared for that one. So we'll have you back, and I know Chris Price, there's questions there for you, and Jorge. There will be also. There's at least one question in there for you. So, Matt, if you can take us to those first initial questions for Christopher Virgil, that'd be great.
No problem. Yes, we've got a question from Coit, who was, is there a version of the graph that you showed which has the GPR time domain, magnetics and borehole distribution on it, or method distribution on it for marine methods? So that is the one that had the sort of depth limits down the y-axis and the amount of urban or urban clutter along the x-axis. Is Christopher still with us?
Yes, he is. He was requesting Lori to unmute him. You're working on that.
Okay, so now
yeah, right. We got you, Chris.
Great. Okay. So the question was regarding the measurements in water.
Yes. Yeah. So have you got a similar chart but showing it for a marine environment?
Okay. Yeah. Okay. This chart is basically for land measurements, but the idea, of course, is the same for sea measurements. Maybe if I start with the second part, how important is it for the German problem? Of course, you have, for example, in the bigger cities, often rivers flowing by or through the city. So in this case, you also have to be prepared to do surveys in the water. Or in the, for example, in eastern Germany, there are often lakes beside the cities, and these lakes were used. A few of these lakes were used for ammunition dumps after or during the World War. So there is definitely an issue here, even with inland water. and necessity to also clear these areas. And there it depends a little bit on the problem here. So for example, with the ammunition dumps, you can assume that ammunition is basically it's a surface of the lake located. So you do not need, in this case, do not need the borehole measurements. But in, for example, Hamburg's harbor area, you also has to do the measurements in the water with toad systems as well as borehole systems. So in this case, it's basically the same. But of course, you're limited with your methods. So for example, GPR in salt water is not so reliable, but then you often use magnetics. But of course, this chart, if we set up a chart for water-based measurements, like the one I showed you, then we have to take this into account.
Mm-hmm. Fantastic. And we had another question from Jeffrey. Are your memberships by company or by individuals?
We would like to have individuals because in our working group, we are trying to focus on really productive work. So it's not about being a member and getting stuff which is researched there and so on. But we really want to have members which are willing to really put in work in the workshop. And so therefore we prefer individuals from companies, of course, so that we have one partner to discuss, to share information with and so on. But of course, this person can spread all this stuff and all the information in the company, which is so also part of the working group then. Yeah.
Fantastic. Yeah.
Okay.
Yes, thank you. Yeah. I can't see any other questions there.
We got one more, or did I miss it? Jan Philip's question?
Mm-hmm. The question regards to how we can help to shape laws with unexploded ordnance detection. Okay, so we are trying to build up a foundation of research-based information which can be used by, as I said, decision makers or operators or other people in a way that you really have some information you can rely on and you can eventually use as a kind of base for either a law, how to apply one method in a certain circumstances, or also for cases where maybe you an accident happened and there's a lawsuit and you can show, no, I have worked based on a certain guideline, our guideline, which is backed up with actual research and stuff like that, so that you can rely on the information you have to either build up your own decisions on, and you can you have documented information. You can foundate your decisions on. So and I think this is the first step, and maybe in a few years then we can help to shape actual laws and try to really get this idea into all the minds which are related with this ordnance clearances.
It sounds like, Christopher, what you need is more of almost like a federal overarching program that pulls everything in from the different states, so you don't have different rules going from state to state within Germany itself.
That's a big problem.
And standardize both the quality control and quality assurance processes. So
that would be good. So that's the main goal, I would say. and to standardize these laws, and also to have one law governs the whole German Republic. So you have not these small scale solutions we have now, or not even these, but this is a long way. So this is not changed in any short period, but we would be very happy if this would lead to this kind of standardization for Germany.
All right, thank you, sir. I don't think we covered Ted Ash's question to Chris Price. So if we can bring Chris Price back in. Chris, Ted's question is, how are you thinking about doing the chemical analysis while in detection mode? And let's see if we can get him unmuted.
The next one we've got is from Johannes for York. What makes the CNN superior over standard 3D EM modeling and inversion methods? Speed, better fit, more accurate characterization of object? Question mark.
Yeah, thanks for the question. I think one of my arguments at the end was it's actually not, I wouldn't say it's superior. It's more like a complementary approach, so a different way of classifying. So that sort of gives us a little bit of room for comparison and see where certain situations where one of the methods is performing a little bit better. And actually, at the moment, we're trying to figure out how to combine these two approaches. Maybe take some pros and cons of each of them and take the best of the two worlds. One advantage I would see is that once it's trained, it's relatively fast to do the classification. So once you already, if you have some way to train your model before going to the field with synthetic data, that actually requires that you at least have the calibration grid, especially because what I explained regarding good estimation of the especially correlated noise, that's we have to put the system on the field at least once in order to get that good estimation. But once you have that part and you train your neural network with synthetic data, you can go on the field and the classification map will be produced very quickly. So that kind of maybe gives us a little bit more real-time classification performance compared to the traditional one that you have to do some manual tuning, picking the anomalies and selecting where you actually detect one anomaly and kind of doing the assigning the class per anomaly. Yeah, that's still, I think it's not fully automated. So that could be one of the advantages. But yeah, as I said, the idea is not one being superior to the other, just taking the best of the two worlds.
And while we've got you online, we've got another question from Sumana. Have you taken into account the corrosion of UXO? What is the accuracy level of this model in real field data?
Thanks. The question was for me, right?
Yes, sir.
Okay, thanks. Yeah, I guess the corrosion would be kind of related with one of the questions that I had before. When I was showing this kind of adding the Gaussian distribution around the mean for a particular ordnance object. So that kind of distribution you can tune to actually account for a little bit of variations in your UXO objects. So that's something that could be taken into account. But of course, it would be a little bit subjective to test. You have to actually have some measurements of the same object with different level of corrosion, and maybe that way you can better estimate that kind of Gaussian or even a different probability distribution surrounding a particular mean of the object that will be like the object in perfect state, right, without any kind of corrosion. And I think that was the first part of the question. There was another second part of the question.
What
yes.
is the accuracy level of the model in real field data?
Oh yeah, that's a great question. So far we have the field data that I showed was for the calibration grid. For that one, our CNN was like 100% accurate. That was the same case for the traditional inversion-based approach. But as I said in the last slides, one of the disadvantages is that we haven't trained our neural network to, for the case where we have two or more objects very close together. And for that cases, we also tried our CNN for what is called the blind grid for sequence-based test site. And there we had this kind of instances where the objects were very close together. And in that cases, since we didn't train our CNN with that kind of situation, we were getting a lower accuracy than the traditional method, but still we managed to get the detection accuracy was more than 95%, and the classification accuracy was also very high. I guess we only get, I think we got like 70, sorry, we only got like 10 false positives. And we, I think we only missed one of the, yeah, I think one of the UXOs. So still, and the traditional approach was 100% accuracy. So there's still a little, we still have to take into account that multi-target scenario in order to increase the accuracy for the field.
Great, fantastic. So I think the last question's for Yuhin regarding, because I can't see any further ones for you.
Yes. So for this question, yeah. So for the testing results, we show are the 2D cases. But yes, this approach can be applied to the 3D inversion. And for now, our study is at the stage of like the feasibility study. We want to test if this workflow does work by using the simple 2D case. And we are working on extended to the 3D inversion, but the GPR data, it doesn't matter if it's collected on the surface or is for the from the cross-hole setup. So there's no limitation of how the data is collected, but the only main limitation I see is still the computational cost. For 3D, the computational cost will be greatly will be a good big problem, right? So that's why, as I just mentioned, we are working on building a surrogate for the forward modeling, because no matter we want to train the neural network or in the inversion, the iterative process, we need to call this forward modeling again. So if the forward modeling is very expensive, then it will this will be the greatest limitation. But we are still working on the surrogate by applying the deep learning technology.
Thank you very much. Right, got a few more questions that have just come in. One from Ted here for you. A general question: is FWI a standard process for GPR analysis, or is it in development?
So is the question for me?
Yes, it is. Yes. Yeah.
Oh, so sorry. I was just drinking water. Could you please repeat it? Could you please repeat the question? Is it in the chat window?
Yes, certainly. I can repeat it. It's a general question: is FWI a standard process for GPR analysis, or is it in development?
So actually, I would say that in practice, I think mostly people use the migration more. But the FWI at least in academia, there are already a lot of work there. So people are working on only no matter the speed or the accuracy, or like from like 2D to 2.5D or to 3D. So this different kind of problem. So the main advantage of using FWI is like it use the full waveforming version, and it can give us the electromagnetic property distribution. So this it means that we can not only we can not only get the location or the shape, but also get the property distribution of the subsurface. So yeah, so at least in academia, there are a lot of work already been done, but in industry or in practice, I think right now the migration is the dominant.
Yes, yeah, I would agree with that. I've seen it used for very specific problems before, for sort of particular engineering tasks and things like that, but not within our survey industry.
Yeah.
I think we've covered all the questions now.
We have covered now we'll open up the floor. Just raise your hand if there's any other questions over the last 3 days. If we still have the speakers, we'll bring them back on, but we'll open the floor up. And while we're doing that, I do want to take time to thank all of our speakers on developing your talks, that you shared your knowledge on the subjects that have been presented over the last 3 days. I especially want to thank the keynote speakers. We had 3 fantastic talks from them, and SEG for putting this on, as well as our sponsors that have helped us help support and reduce the cost for registration. So, and technical committee, Jeff Lieberfinger and Michael Kalinsky, to helping to review all the abstracts and get us to this point. And I do see some hands coming up, Matt.
Sorry, I need to change my view to
No, I know. I'm tempted to do the same to mine. Garrett. It looks like Garrett is. August has his hand up, and his speaker should be live, or microphone should be live.
Yes, can you hear me?
Yes, sir.
Wonderful. I was just curious about where we can find the recordings after this.
Lori, can you speak on that?
Yep, you will every registered attendee will receive a link to access the recordings.
Okay, I saw a question come up. Will contact information for the personnel be available? Lori, are we able to do that or not? Once again, the question is, will contact information for other attendees be shared to facilitate collaboration?
Yeah, I don't believe I have privilege to share personal information.
Yeah, I tend to agree with that.
But if you email me, I can ask whomever it is that you want to contact if they're willing to share their email. And also LinkedIn is a great resource. That's how I found all of you. No, just kidding. But yeah, just email me and I can reach out to that person. If they are willing to share their information, I'm happy to share it.
And Lori, if you can bring up our sponsors once again. I do want to thank NAOC and Aegis for helping us here, and especially SEG for putting on the summit.
Andrew, just to reiterate, the video recordings will be emailed out to all the delegates.
The link to the recordings.
So TemSense, Geonics, and Sequence. Thank you again. And that will conclude the summit for 2024. Thank you to all the attendees and the speakers.